Hello everybody, welcome to my channel VKS Chem tutorial. In the last video we have discussed the important characteristics of pericyclic reaction, classification of pericyclic reactions and examples of each class of pericyclic reactions. Today I will discuss the methods of analysis of pericyclic reactions. You know, the important methods of analyzing pericyclic reactions are correlation diagram method, frontier molecular orbital method, Huckel-Mobius analysis or PMO method. These are the important methods using which we can analyze a pericyclic reaction, different types of pericyclic reaction. Correlation diagram method, frontier molecular orbital method or FMO method, and Huckel-Mobius analysis or PMO method. Using any of these methods, we can analyze and predict whether a particular pericyclic reaction is feasible under given condition or not. Okay. Remember what are the important classes of pericyclic reactions. The important classes of pericyclic reactions or types of pericyclic reactions are cycloaddition reactions, electrocyclic reactions, sigmatropic rearrangement, chelotropic reactions, and ene reactions. Among them, cycloaddition reaction is an important type of pericyclic reaction. All these pericyclic reactions can be analyzed either of these methods such as orbital symmetry conservation method, orbital symmetry correlation diagram method or orbital symmetry correlation, or FMO method, that is frontier molecular orbital method, or Huckel-Mobius method, otherwise called perturbation molecular orbital method, that is PMO method. In this video, we will discuss orbital symmetry correlation diagram method for analyzing cycloaddition reaction. Here we will discuss the 2+2 cycloaddition reaction using orbital symmetry correlation diagram method. Right? Then what is correlation diagram method? In correlation diagram method, we are correlating the molecular orbitals with a particular symmetry property of the reactant orbital with the molecular orbital with the same symmetry property of the product and vice versa. That is, if the symmetry properties of the ground state molecular orbital of the reactants are correlating with the ground state molecular orbital of the product and vice versa, the reaction will be thermally allowed. That means if the molecular orbitals in the ground state of the reactant with a particular symmetry property are correlating with the ground state molecular orbitals with that symmetry properties, then the reaction will be thermally allowed. That is, the ground state molecular orbitals of the reactants with a particular symmetry properties are correlating with the ground state molecular orbitals of the product and vice versa. Reactant molecular orbitals are correlating with the product molecular orbitals in the ground state each other. Okay, then the reaction is thermally allowed. But if the symmetry properties of the ground state molecular orbitals of the reactants are correlating only with the excited state molecular orbitals of the product and vice versa, then the reaction will be photochemically allowed and thermally forbidden. That means if the ground state molecular orbitals with a particular symmetry properties of the reactants are not correlating with the ground state molecular orbitals of the product, instead it correlating with the excited state molecular orbitals of the product and vice versa, then the reaction is photochemically allowed and thermally forbidden. The reaction is photochemically allowed and thermally forbidden. Okay. Now let us consider the correlation diagram method of analysis in cycloaddition reactions. Remember, cycloaddition reactions are those pericyclic reactions in which two or more pi system adds together to form a cyclic adduct. Two or more pi system adds in cycloaddition reactions to form a cyclic adduct. In the case of 2+2 cycloaddition reaction, two ethylene molecules are added together vertically to form cyclobutane. Cyclobutane. When these two ethylene molecules approach each other, this molecule or this system will have a plane of symmetry, referred to as sigma h, that is horizontal plane, sigma h, or it is otherwise referred to as 1, and a vertical plane of symmetry, that is sigma v, otherwise represented as 2, that is plane 2, sigma v or 2. And the product cyclobutane also has same element of symmetry. There is sigma horizontal plane, that is sigma h, and a vertical plane, Okay. Hence the analysis will be based on these symmetry properties, the horizontal plane of symmetry and vertical plane of symmetry of ethylene molecules and cyclobutane molecules. In the case of 2+2 cycloaddition, where ethylene molecules interact each other vertically, each of the ethylene molecule has a pi bond, and these two pi bonds in two ethylene molecules gets converted into two sigma bond in cyclobutane. Otherwise, we can say each of these pi bond in each ethylene molecule consists of two pi molecular orbital, one pi bonding molecular orbital, another pi star anti-bonding molecular orbital, and hence there are 4 pi molecular orbitals in these two ethylene molecules. That is 2 pi bonding molecular orbitals and 2 pi anti-bonding molecular orbitals. These 4 pi molecular orbitals are interacting together to form 2 sigma bonds or 4 sigma molecular orbitals in cyclobutane. That is what actually taking place during this reaction. That is 4 pi molecular orbitals of 2 ethylene molecules interact to each other, forming 4 sigma molecular orbitals in 2 sigma bonds in cyclobutane. Okay. And these 4 pi molecular orbitals, pi 1, pi 2, pi 3 star, that is anti-bonding molecular orbital, and pi 4 star, that is another anti-bonding molecular orbitals, altogether 4 pi molecular orbitals, combining in 4 different ways. There are possibility for the combination in 4 different ways. The ways of combination and the symmetry properties with respect to these combinations, such as horizontal plane of symmetry and vertical plane of symmetry, are represented like here, like this. Okay. For example, you can see it is pi plus pi, that is pi plus addition. Combination is addition, plus 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 plus. All these lobes are equivalent or similar, and hence they are combined by addition, that is pi plus pi. Then here minus plus, that is subtraction. This combination is subtraction process, that is pi minus pi. And this combination you can see it is antibonding molecular orbital, that is plus minus antibonding, plus minus antibonding, and this combination is addition combination, that is plus plus minus minus. But these molecular orbitals are antibonding, plus minus. You can see by their lobe signs, plus and minus, and so it is an antibonding molecular orbital. Their combination is an addition combination, that is plus plus minus minus. Similar lobes are orienting in the same side, and hence it is an addition combination, that is plus pi star pi star, pi star plus pi star. Here it is another antibonding molecular orbital, plus and minus. Here also minus and plus, and so these are antibonding molecular orbitals. The combination is also subtraction, that is plus minus, so it is subtraction combination. And so 4 types of combinations are possible here, and these combinations will have the elements of symmetry such as horizontal plane of symmetry and vertical plane of symmetry. You can see here it is marked as 1 and 2. The symmetric and anti-symmetric is represented as S and A. Here first we are looking into the symmetry properties with respect to 1, that is horizontal plane of symmetry, that is marked in first in the bracket, and the vertical plane of symmetry is in the second in the bracket, which is represented either as S or A, S for symmetric and A for antisymmetric. So you can see here in the first case it is horizontal plane, there is a horizontal plane of symmetry. Here plus plus, if we look into this plane of symmetry 1, you can see identical structure, it is the mirror image of this, and so it is symmetric with respect to horizontal plane of symmetry. If we are looking into the vertical plane of symmetry, then it is 2. It is also this part, this half is the mirror image of this half, and so it is also symmetrical. And in the second case, first of all we have to look into the horizontal plane of symmetry. It is anti-symmetric. You can see minus plus, it is not identical. These two molecular orbitals are not identical, and so it is anti-symmetric with respect to horizontal plane of symmetry 1, and with respect to vertical plane of symmetry 2, you can see this half is the mirror image of this half, so there is a vertical plane of symmetry, so it is symmetric with respect to vertical plane, and so S. And for this combination, horizontal plane of symmetry, it is identical with respect to this, and so horizontal plane of symmetry is symmetrical. But if we are looking into the vertical plane of symmetry, then you can see this half is not identical with this half. This half is not identical with this half. So there is no vertical plane of symmetry, and so vertical plane of symmetry is anti-symmetric. And in the last case, horizontal plane of symmetry, that is, this is not identical with this molecular orbital, so it is anti-symmetric. Then vertical plane of symmetry, it is also anti-symmetrical because this half is not identical with this half, and so it is also anti-symmetric with respect to vertical plane of symmetry. That is how we can represent or assign the symmetry properties with respect to the element of symmetry such as horizontal plane of symmetry or vertical plane of symmetry in molecular orbital. Here in the case of pi molecular orbitals of ethylene molecules. Okay, here we have seen that 2 pi bonds of ethylene molecules gets transformed into 2 sigma bonds in cyclobutane, or otherwise we can say 4 pi molecular orbitals of 2 ethylene systems gets transformed into 4 sigma molecular orbitals in cyclobutane. That is sigma, sigma, sigma star and sigma star, 4 sigma molecular orbitals in cyclobutane. And these 4 sigma molecular orbitals combine together in 4 different ways, as in the case of ethylene molecules. These cyclobutane molecular orbitals also combine in 4 different ways. It is represented here. And these sigma molecular orbitals may be symmetric or anti-symmetric with respect to the horizontal plane of symmetry and the vertical plane of symmetry. Horizontal plane of symmetry 1 and the vertical plane of symmetry 2. As in the case of ethylene bimolecular orbitals, here we can represent the first letter in the bracket as indicating the horizontal plane of symmetry, whether it is symmetric or anti-symmetric, and the second letter in the bracket usually represent the vertical plane of symmetry, whether it is symmetric or anti-symmetric. See, in the first case, here sigma molecular orbitals are combined, or this combination is addition combination, sigma plus sigma, it is addition combination, plus 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 plus. So addition combination of sigma molecular orbital. See, you can see there is a horizontal plane of symmetry. This half is the mirror image of this half, and so it is symmetric with respect to horizontal plane of symmetry. Also, you can see if we place a vertical plane here, this half is the mirror image of this half, and hence the vertical plane also symmetric. S with respect to horizontal plane, and this S with respect to vertical plane. And the second combinations, it is you can see plus plus, minus and minus, and so it is subtraction combination. And this subtraction combination, if you place a horizontal plane here, you can see this is the mirror image, this half is the mirror image of this half, so it is symmetric with respect to horizontal plane. And if you place a vertical plane here, you can see this half is not the mirror image of this half, it is minus minus, it is plus plus, so it is anti-symmetric with respect to vertical plane of symmetry. So it is A, the second letter is A, that is symmetry with respect to symmetry properties with respect to vertical plane of symmetry. Then in the combination 3, that is sigma star molecular orbitals are added. So sigma star plus sigma star. If you place a horizontal plane here, then you can see this half above is not equivalent to this half, or it is not the mirror image each other, so that it is anti-symmetric with respect to horizontal plane of symmetry. Then vertical plane of symmetry, you can see this half is the mirror image of this half, and so vertical plane of symmetry is symmetric. And so in the last case, if you play, it is subtraction combination of sigma star or anti-bonding molecular orbitals, subtraction plus minus, so it is subtraction. So you can see if we place a horizontal plane here, you can see this half is not identical to this half, so it is anti-symmetric with respect to one or horizontal plane. And if you place a vertical plane here, then you can see this half is not identical with this half, so it is not the mirror image to each other, so it is anti-symmetric with respect to vertical plane of symmetry. And so we had already determined the symmetry properties of interacting molecular orbitals of ethylene molecules, and also interacting molecular orbitals of cyclobutane molecule with respect to horizontal plane of symmetry and vertical plane of symmetry. Okay, that is the first step in correlation diagram method of analysis, right? After discussing, after determining the symmetry properties of the 4 pi molecular orbitals of two ethylene molecules and 4 sigma molecular orbitals of the cyclobutane, a correlation diagram can be constructed for ethylene cyclobutane interconversion. Okay, in which the molecular orbital levels of like symmetry of the reactants are connected to that of the products by lines. Okay, it is the correlation diagram for interconversion of the two ethylene system to cyclobutane. The forward reaction is cycloaddition reaction, while the backward reaction, the ring opening, is cycloreversion reaction. Ring closure is cycloaddition and ring reopening is cycloreversion reaction. It is the correlation diagram where the molecular orbitals with respect to the horizontal plane of symmetry and vertical plane of symmetry of 4 pi molecular orbitals in two ethylene molecules and 4 sigma molecular orbitals in cyclobutane are represented, and symmetry properties with like symmetry are joined by lines. Then you can see here it is the left hand side molecular orbitals are molecular orbitals with the symmetry properties of ethylene molecules, and in the right hand side this is the symmetry properties of molecular orbitals of 4 sigma molecular orbitals of cyclobutane with respect to horizontal plane of symmetry and vertical plane of symmetry that we had already discussed. Here pi 1, that is SS, pi 2 AS, pi 3 star SA and pi 4 star AA. The first letter is with respect to horizontal plane of symmetry and the second letter is with respect to vertical plane of symmetry. Here sigma 1 SS, sigma 2 SA, sigma 3 star AS and sigma 4 star AA. First of all, we have to join the molecular orbitals with similar or like symmetries with lines. Then you can see SS are joined by lines. Then AS, here is not a AS, but here is AS and AS symmetry properties with like symmetry or molecular orbitals with like symmetry are joined by lines. Here SA, here is an SA. So SA and SA molecular orbital symmetry properties are joined. Then AA and AA. This correlation diagram indicates the ground state molecular orbitals are not correlating with the ground state molecular orbitals. Here, even though these two ground states are correlating each other, but this ground state correlate with the excited state molecular orbital. Similarly, this ground state molecular orbitals of the product correlates with the excited state of reactant, and hence we can say the molecular orbital symmetry properties of ground state molecular orbitals of reactants are not correlating with the molecular orbital symmetry properties of the ground state molecular orbitals of the product and vice versa. So it is thermally forbidden reaction. It is thermally forbidden reaction. The 2+2 cycloaddition reaction is thermally forbidden. This correlation diagram indicates that 2+2 cycloaddition reaction is thermally forbidden because the ground state molecular orbitals are not correlating with the ground state molecular orbitals of the product and reactants each other. Okay, instead one of the ground state molecular orbitals correlate with the excited state molecular orbitals of the product, or one of the excited ground state molecular orbitals of the product correlate with the excited state molecular orbital of the reactant and vice versa. So this process, the 2+2 cycloaddition reaction, is photochemically alone. Ground state is correlating with the excited state. Here the ground state is correlating with the excited state. And so The reaction taking place after excitation process. So it is photochemically allowed and thermally forbidden. 2 plus 2 cycloaddition is photochemically allowed because the ground state is correlating with ground state molecular orbitals of the reactant is correlating with the excited state molecular orbitals of the product and vice versa. So it is photochemically allowed process, and the ground state molecular orbitals of the reactants are not correlating with the ground state molecular orbitals of the product and vice versa. So it is thermally forbidden. In general, 2 plus 2 cycloaddition reaction is thermally forbidden but photochemically allowed. Okay, that is the result. The same result can be indicated like this also. That is pi 1 square, pi 2 square. That is the ground state molecular orbitals of the reactant, where the total 4 pi electrons are occupying 2 electrons each in pi 1 molecular orbital and pi 2 molecular orbital. That is the ground state. Here, that is not correlating with the ground state molecular orbitals of the product, that is sigma 1 square and sigma 2 square. That indicates the 4 sigma electrons should be occupied in sigma 1 orbital and sigma 2 orbitals, but it is not the case, and hence it is not correlating each other. Hence the thermal process is symmetry forbidden. Okay, then otherwise it is represented like this: pi 1 square, pi 2 1, pi 3 star 1. That means one of the electron here jump from pi 2 molecular orbital to antibonding pi 3 star. That is correlating with the sigma 1 square, sigma 2 1 and sigma 3 star 1. That means one of the electron will jump from sigma 2 molecular orbitals of cyclobutane to sigma 3 star antibonding molecular orbital of cyclobutane. That is correlating. The symmetry properties are correlating here. That is the ground state molecular orbital or electrons gets excited. This indicates electron gets excited. Excitation process takes place during the photochemical process. So the 2 plus 2 cycloaddition is thermally forbidden and photochemically allowed. That is the analysis of 2 plus 2 cycloaddition reaction by correlation diagram method. Okay. Yes, I think you might have got a clear idea about how to analyze a cycloaddition reaction with the correlation diagram method. Okay. With this discussion, I conclude my video here. In the next video, I will discuss the 4 plus 2 cycloaddition reaction and the method of analysis of 4 plus 2 cycloaddition reaction, which is a very important reaction known as Diels-Alder reaction by correlation diagram method. Okay. Thank you for listening. Thank you.